Open your SAP. I'm going to create a very simple model, like this beam that I designed on the Blackboard. Okay, now you are able to use SAP, so I can go quite fast. Blank, new model, grid only. Edit grid data and modify system. The beam is HEA 280. And the length is 6 meters. Double supported, double pinned. Simple supported with an axial load. So first of all, I want to check what is the limit, the buckling. So I can start with a buckling analysis. I'm going to create the grid. We can perform just a planar analysis in X and zeta. So just a grid with 1 meter in X and 6 meter in zeta. If you go in the X zeta plane, you will see something like this. And if you remember, to perform a planar analysis, you have to select an option in Analyze, Set Option, and you can select the X zeta plane. So as I told you last time, we don't have displacements out of plane. So also the buckling out of plane is not considered. As usual, I have to define the material. Add new one. Italy, of course. Okay, 210 gigapascal. And Poisson 0.3. Again, also in this analysis, it's not important the material, because it's a non-linear analysis, of course, but there is nothing that depends on the material. It's only geometrical effects. So here you can leave this material or you can change, it's not important. And as usual, I have to define the section, the cross section. The imported one, Europe, go to find HEA 280. Okay, this is my cross section. I'm going to leave everything without modify anything. Pay attention to assign the material that you have created. And this is the cross section. we can design the new beam, straight frame, design using the strong axis in the plan. The mesh for the second order analysis is really important because you must catch these effects or these effects. So if you don't create a refined mesh, you can imagine that it's impossible to calculate these effects for the software. Okay, if the software have inside a refined formulation, a refined beam formulation with intermediate integration point, maybe you can do it, but it's better to create a refined mesh.
How many elements do you have?
6. Six elements of 1 meter. Okay, now we can define the load. We can calculate, for example, first of all, the buckling. Starting from the inertia. This is the buckling, in-plane buckling, will be a double supported beam. We have a double symmetrical cross-section, so the buckling will be flexural buckling. This is, of course, the strong axis because we don't have out-of-plane displacement. So if you perform the buckling analysis, your buckling, your force buckling will be a flexural buckling equal to the ratio between these two values. More or less it will be 12.1. So I expected from the buckling analysis 12.1. So we can define the boundary condition, joint restraint, as you know, double supported condition, so I'm going to fix the translation on one end and fix translation leaving the actual displacement on the other end. And in the end, where you leave the free displacement, you have to apply the load. Because if you put the actual load in the other end, of course, you will have not. If you put the actual forces here, the forces go directly on the ground and not on the beam because you don't have displacement. Okay, before assigning the load, we have to create the load case, load pattern and load case. We can create force, self-multiplier 0, because I don't want to consider self-weight. And you can create a live load. Okay, we can assign the load. (650 kilonewtons), so 650,000, because here I am in Newton. Sorry, in compression, of course. Okay. And I'm going to define buckling analysis to check the buckling multiplier. If you remember, buckling in the lowered case definition, add the forces with the scale factor 1, then buckling mode, and run. Of course, you have to save with a new name. Okay. The first buckling is a flexural buckling. That you have the whole length of the beam in buckling, and the factor is 11.59. You know that is quite different because the shear deformation. We can remove the shear deformation and obtain the exact value, but now it's not important because I want to check the second order effects. So I'm going to write directly the buckling multiplier. So the fourth buckling mode is something like this, and the mode is 111.5. .6596. Okay, look at the second mode. Second mode is a mode always flexural, of course, but the length is not the whole length of the beam, but is half. So if you want to calculate this mode in the equation, you can modify this length. Put 300, 3000, because it's the half length. Or you can use the theory that gives you this mode is multiplied by a number that is n, when n is the first mode is equal to 1, when n is the second mode is equal to 2. So in this time, by leaving the same buckling length, you will have n equal to 4. So this mode must be 4 times the first mode. The second mode must be the 4 times the first mode. In fact, if you look at the multiplier, it is 41.54. this the buckling length here is 6 meter, and here the buckling length is 3 meter. The ratio between these two modes is more or less 4. It's not exactly 4 because again we have shear deformation and different effects. If you consider only perfect Eulero-Bernoulli beam, you will see that this ratio will be exactly 4 times. Okay, now we find two different modes. I can use this graph and put here my beam. Put here the first mode and the second mode. Now we can perform the second order analysis by considering perfect beam being deformed with the first mode or beam deformed with the second mode. We can start with the perfect beam, so you don't have to modify anything. You have just to create the nonlinear case, so load case, add new load case, is a static load analysis, but nonlinear analysis, like the one that you used for the computation of resisting tension only element, that was nonlinear analysis. But this time you have to consider p-delta effects. That means consider the geometrical matrix inside my analysis, consider p-delta effects. You can see here you have the option also to consider the more advanced analysis, p-delta plus large displacement. But SAP itself says do not use this analysis because it's not working. So use always p-delta effects only in SAP. If you have OpenSys or other software, you can use large displacement because they are validated. Okay, the scale factor is 1 and we have to add the forces. These options are really important because we influence your results, because a second order analysis is a nonlinear analysis performed by iteration. So you can change the step of, if you want to study this behavior, you can change the step of the iteration and you can change the convergence criterion. I don't know if you study numerical method. Normally, these analyses are resolved by using Newton-Raphson method, that are method that gives a first attempt, then do some iteration to find the right solution. Is a try and error method. But the Newton-Raphson method is not able to give you this softening behavior because it's filed when the curve is almost linear. So for the softening behavior you need an arc length. Arc length is a method that searches the solution around a length, around an arch of a prescribed length. But these are numerical questions. If you want to know more about numerical questions, you can write me, then we can meet. But it's not the scope of the course to talk about numerical method. For this kind of simple analysis, you can leave this option by default. These are really important when you have a very complex situation with the contact, with a very, very big model with very particular behavior. We can rename the case, second order. No. We can also create a first order case to check the differences. For the first order, you just have to create the linear case, static linear. And I can also add another second order case and amplify the scale factor 10 times to see what's happened on my beam. So this second case, I have the scale factor 10 times greater. I don't know how many cases I can have in my evaluation license, but in the complete one you can add like 1,000 cases. I'm going to add also another case with 15 times. Second order, 15 times. Okay. First order, we don't have any lateral displacement. We have a displacement of 1.9 on the top, and we don't have any bending moment. We have only axial forces. I'm going to check the first second order case, that is with the multiplier equal to 1, and again you can see we don't have any bending moment. And if we look at the displacement, second order case, is exactly the same calculated by the first order, and we don't have any lateral displacement. So I performed an analysis on the perfect beam, and I obtained a displacement that is here, because we don't have any lateral displacement. Delta is the lateral displacement. What's happened when I amplify 10 times the load? The displacement is exactly 10 times higher. And I don't have again any lateral displacement. So I'm here. If you remember, this is 11.6. On the deformed shape, on the perfect beam, I can go over the backing load, because if I look 15 times the displacement, you can see that displacement is exactly 15 times with no lateral deformation. So I'm here. What it means? I performed a second order analysis, but I don't have any deformation, I don't have the delta effect, so I can go wherever I want on this vertical line. But now the interesting part is what's happened when I impose a deformation. Start with the forced mode by imposing a forced buckling mode of, as you know, the buckling mode are undefined displacement, because everything in the buckling mode, like in the modal mode, are scaled by a scale factor. So from the buckling analysis, you don't have this value. You have only the proportion from the middle displacement and the quarter displacement. The proportion is the same, but the displacement can be everything. So you have to impose an initial value of the maximum displacement, and you can update the configuration by using the buckling mode. I can put 10 millimeter. In some software, you can just select forced mode, amplify the mode by 10 millimeters, and update the model. So it's really simple because you don't have to modify anything. In SAP, this is not possible, so I have to create a curved beam. So I'm going to create a curved beam. You can delete everything. When you draw now the frame, here pay attention, do not select straight frame, but curved frame. Here, you can see curved frame, the second option. Once you select the curved frame, you have just to select the first and the last point, and then you will appear this kind of menu. This is a circular arc, okay? First coordinate are 0, 0, 0, the lower point. The upper point is 0, 0, 6 meters. The middle point is 0, 3 meters of 8, and 10 millimeters in the x direction. So we have 10 millimeters here and 3 meters here. That means in the middle we have 10 millimeters in the x, and in the middle, so in 3 meters of 8. So this is the results. If you zoom on the 3 meter 8, you will see that it's not straight, but you have this displacement. You cannot measure because I think you cannot select this point, but more or less are 10 millimeters. SAP divided automatically the curved beam into different elements. You can be sure and gives to this frame the automatic mesh option. So frame, automatic frame mesh. and you can put the minimum number of segments that are 10 or I don't know if it's no, maybe it's better to leave as it because I don't know if the put a very big number like 20. Okay, once we have our beam, we can create the boundary condition and apply the load. The same, the previous boundary condition, the previous loads. So again, assign external restraint. On the bottom, everything, the translation are fixed. On the top, we leave free the axial displacement. And we can assign the loads. The same 650 kilonewton. We have just defined the second order analysis. Now do not perform the first order. Perform just the second order with the multiplier equal to 1. And the one with the multiplier equal to 10. Okay, now you can see that for the second order analysis, we have lateral displacement, of course. The axial is quite the same, but we have also in the middle why don't give me okay a displacement of starting from the deformed position of 0.95. Okay, so we put the load equal to 1, so is 1 times, it can be here, no, lower, and we obtain 0.95. If we look at the load equal to 10 times, sorry, not the bending moment, the displacement. The displacement is 64, so it's not 10 times, but it's greater, because from the 0.9 became 64. So in this point I have something that is 64. So I have something like this. What's happened if you perform the analysis with the load 15 times greater? You can see the beam changed the configuration. So became from the plus 64 going to the minus. I can do by using different steps to be more clear. I'm going to add different steps. $11. And I can add 13. So I created an iterative analysis manually by manually put the increment, put the vertical load that can increment step by step. You can do also automatically this kind of analysis.
Because that's what we did with the step.
Yeah, it's a multi-step analysis created by hand, but you can do also by automatic in the software by changing that parameter that I leave by default. Okay, starting from the displacement of 10, you can see 64, this point. Then you can see 192. So with a really small, because here was 10, the step after is 11, so with a small load we have a very big displacement because it's more than 3 times. So it's something like this. And this is what I expected because the buckling mode is 11.6 and now I amplified by 11. So we are in the plateau. If I put 12, you can see that the displacement is changed. Change the direction. And became minus 94. So it's something like this. And then the software finds the equilibrium but in a different position. Sometimes if you run a multi-step automatic analysis, maybe you will see only this 94 value. So and you will see, okay, 94 is a good displacement for me. And you are not considering that this is not the forced equilibrium position. Because in the forced equilibrium position you have a displacement that is quite infinite. So this is really important to understand the load history. Because maybe your limit is not 11, but something like this 10 or something like this. Instead, if you perform an automatic analysis, maybe you can say, okay, also 12 is acceptable. And if you increase again the load, the displacement increase in this new equilibrium position. So this is with the first buckling mode. This is 11, the limit. What's happened if you put here instead 10, 100? The limit is always the same, but it changed the initial stiffness of your curve. So it changed the initial displacement. So you will have something like this. Maybe reach the same final displacement, so something quite something like this. So you will reach the same limit of the vertical load, but with different path. Okay, now we can try what happened with the second mode by using the second mode. Remember, this is the shape of the second mode. I'm going to put 10 millimeter on this displacement. And we can see what's happened. So I will delete everything. You can create two curved elements. The first one from 0 to 3 meters by having 10 millimeter on the half length, so 1 meter, 0.5. And the other one by having minus 10 millimeters on the half length, that is 4 meter and 0.5. I can write here better for you. From 0 to 3, we have plus 10 on 1.5. From 3 to 6, we have minus 10 on 4.5. This is your beam. I'm going to define again the restraints that are the same. And again the vertical load. That is the same. Okay, I can leave the same case to understand what happened. Of course, this is the deformed shape, so it's different from the previous one. The maximum displacement, if you remember, previous was 0.9. Now I can take the positive one. It's 0.25, so it's smaller, so it's here. So something is changed. When I amplify 10 times, if you remember, the previous displacement was 6.4, now is 3.2. So here we have this kind of displacement, 3.2. If you remember, with the first mode on the 11, we have some like the plateau with 200 of displacement. Now we can check the maximum displacement, that is 3.6, so it's really small. It's something that is here. I can go by increasing the load. You can see the displacement still increase, but very, very small value. You can see also in the 15 we have 5.8. So at the end of the day, what's happened? With the second mode, the plateau is not this one, but the plateau became the plateau related to the second mode. This is really important because here is not scaled, the graph. Because this is 4 times higher, because this is 42. But you can see in this range, if the imperfection is the second mode imperfection, in this range the displacements are quite very small, quite linear. Becomes linear after very, very big value of the axial load. If I put the one that is for example 40, at 40 I expected very big value of the second order displacement. You can see at 40 I have 300, and so at 40 I have the plateau. Again, if I increase again the load, I will obtain the change of the deformed shape and the change of the sign of the displacement. So at the end of the day, what's happened on my beam? Because in the real life we don't know the buckling shape. If you try at home to start a second order analysis on a beam that is a combination of these two modes, or the fourth, the second, the third, on beam that is something like this one, or on some more complex than this one, if you combine, I can explain just combining the first and the second mode. So here we have plus 10, minus 10, here we have 10. So the deformed shape is something like, in the middle is 10, here is 20, sorry, this will be like 5 more or less, so this is 15 more or less, and here is -5. So it's something like this. Okay? If you perform a second order analysis on this beam, what you will observe? You will observe that until here, until the first mode, you will have some displacement that is similar to the first buckling mode. That your beam will deform in this direction by following the first buckling mode, and then something happened, change the configuration and start with the second buckling mode. But for the design point of view, we are interested only on this limit. Because we don't want to enter into post-buckling behavior. So this is why the codes give you some reference on the buckling and limit the buckling behavior of your frame. Did you perform the analysis?
Alla fine,
Senza curvare.
si qualcuno muoio.
Ah, quello sì, ok. How to estimate second order effect manually? Pay attention that this kind of analysis, you have to perform always this kind of analysis if your buckling is lower than 10. You have always to perform second order analysis or using a amplifying factor that depends on the buckling. This means something like what this means. If you have a frame, you want to design this column, for example, you have to amplify the value of the bending moment by this factor. So the second order bending moment is the first order amplified by beta. The limit of using beta is alpha lower than 3. Because when alpha is 3, this became 1.5. This is the limit of this term. manually we can use also the lateral equivalent lateral force method. Equivalent that is an iterative method. We can talk about this method. Pay attention from this equation, lower is the critical load multiplier, higher are the second order effects. That means if I have a rigid structures or a flexible structures, here I have everything with the rigid joint, here I have a pin-head connection. This is more rigid than this one, so this alpha critic is greater than this one, so alpha, this can be like 20, and here can be like 3. That means in this kind of structure you don't need to perform second order analysis, or if you want to perform second order analysis, the effects are very lower. Low effect of second order. In these structures you must perform second order analysis, and the effects are really big effects. Pay attention that also when we talk about second order analysis is not only for this kind of linear analysis or something, but also for the modal analysis. So these very flexible structures also in the seismic behavior are very flexible. So if you want to calculate the modal analysis to calculate the period of the structures, I can write something like this for the modal analysis. This is the mass matrix. In this elastic you must consider second order effects. That means that the period calculating by on these structures the first order period is practically equal to the second order period. But in these structures you will have that the first order period is different from the second order period. Is more flexible, this structure, so the second order period is greater than the first order fundamental period. So in a spectrum, with the first order analysis you can be here, with the second order maybe you are here. We can try to do another exercise to understand the second order effects in another kind of structures. And I can validate this beam by using never use this procedure in a frame because it's becomes crazy. We can check the results of SAP. We have just defined the material that is elastic and blah blah. 210 gigapascal, 0.3 Poisson. We have just defined the cross section that is the same, HEA 280A. So we can create the straight beam, not curved this time. I create 6 elements beam. This time I'm going to remove the shear deformation because I want to see good results. So the condition is fixed on only one end. Of course, this analysis is a planar analysis. I consider the buckling and the imperfection in this direction, only in the planar direction. Pay attention that putting a force here is like to give to my beam a deformed shape. Is equivalent. In the Euro code, the imperfection, you can give the imperfection by using a deformed frame or by using equivalent forces. So I did the same thing. I give to my beam an initial configuration with forces, so a deformed shape configuration. Okay, first of all, I'm using the load. Okay, I can create. No, I can use the same load pattern force that I have created before, and I can assign the loads on the free end, of course. So I have axial forces on compression, I have lateral forces, and bending moment. Pay attention on the unity, that is, this is Newton millimeter, so 40 multiplied by 10 for the power of 6, by the power of 6. This is 640 power of 3 and 10 power of 3. Of course, the bending moment is in the y direction because we have zeta x and y is out of the plane, so the bending moment is in the y direction. If you look in the planar view, you cannot see the bending moment, so you need the 3D view to see also the bending moment. So we can perform. I'm going to recreate everything. So we can perform a static analysis, linear analysis, second order analysis, and buckling analysis. Okay, check the buckling. buckling is perfect, 3.07. That is exactly the one number if you do the ratio between these two. I expected that the buckling is a flexible buckling in this direction, as I show you in the lecture on buckling. Okay, this is the flexural mode. We can check the first order displacement. That was 50.2. Okay, it's perfect, 50.16. We can check the bending moment, the first order bending moment. You can see here it's perfect, 100 kilonewton meter. And last thing, we can see the second order effects. Starting from the second order displacement. (73), so is quite greater than the one that I have calculated by hand. (73.6). And the internal bending moment that is quite greater, but is exactly more or less the same, because I obtained 146 kilonewton meter. Also, the differences here is lower than 10%. So you can see that the second order effects can be calculated automatically by considering in the sub this option, second order P delta effects. What's happened if I increase only the axial load? I expected the same first order displacement and bending moment, but greater second order effects, because the buckling changed. I can show you, assign new load condition. If the limit is 3 times, if I put here something like is multiplied by 2.5, now the buckling will be lower. Buckling, as I told you, is linear, so 3.07 divided by 2.5 is exactly 1.228, and the buckling is 1.229, so the new buckling is 1.22. What it means, if we look again to our Q, in the previous condition we are more or less, we were here. If we look at the opposite, if the buckling here is 1, now with this value we are in the plateau more or less. to expect very, very big second order effects. We can start checking this first order effect that must be the same, the previous one. You can see that are exactly the same, 50.2 and 100 of bending moment. (100 kilonewton meter). Okay, but second order now. From 73 becomes now I think this changed the configuration. I must put some smaller, sorry. Ah, no, because okay, sorry, I changed the unity. I reassign again the one 2.5 greater. I didn't understand the values, okay. Okay, Newton millimeter. If we look at the displacement from the 73, we obtained 270 now with this new buckling. And for the bending moment, we have a very, very big bending moment, 532.6. That means 4 times greater than the one. 5 times, because 100 is 5.3 times greater. So in this case, the second order bending moment is 5 times 0.3 greater than the first order bending moment. If we try to use the beta terms, it's not allowed for you from the code, but we can see that more or less you can obtain 5.5. So with this term you can have an idea of the second order importance on your structures. But pay attention that very small increment of load in these zones will give you a very bigger influence of the second order effects. What's happened when the frame changed the buckling configuration? Of course, the bending moment will change its sign from the positive to the negative, or it start to reduce instead of increasing, because the displacement changed the position or became smaller instead of greater. Of course, if you have no axial forces, with no axial forces, as you know, buckling doesn't work in SAP with no axial forces. With no axial forces, you can see that the first order displacement, that is always the same, 50.16, is perfectly equal to the second order one. This is the linear 50.16, and the second order 50, perfectly equal, because P delta effects, of course, depends on P. If you don't have P, you don't have P delta effect. You can see bending moment is equal in the first and in the second order. Question about this analysis? Prima era il carico critico diviso carico fisso, semplicemente prendere il carico diviso carico fisso. Quindi quando sì, cioè di là riportava il carico critico direttamente, invece qui era fuori il rapporto tra il critico e il carico fisso. No, carico, cambia. Perché se questo incrementa, vabbè, comunque il concetto mi fa. Cioè, aumentando il carico sempre vicino al carico critico. Uno se ne carica. I will show you on when I will talk about the pushover. And it's sometimes for me the pushover analysis. Okay, last thing about second order effects. I think everything is clear. Now we have finished the basic analysis because now we are able to perform everything. So the next time we can see a complete frame, a design of a complete frame by using second order analysis, first order analysis, and elastoplastic analysis. From the hero code, we have more or less 4 different methods of analysis of a frame. First one, Eurocode say to you, take a frame and insert into the frame all the imperfections. So, out of plane of the element, plus non-perfect or curved beam. From a practical point of view, in your model you can design this really complex model. So you can take your frame, give a an initial out of plane. This depends on the term phi. This is called E with 0. But there is no automatically. Yeah, in Consteel you can do automatically this kind of implementation. You can say that give to a global drift to my frame of phi equal to some values, and give an initial drift to my beam of an initial value. You can do automatically. In SAP you have to design curved beam and displace the deformed frame. So Eurocode allows you to insert equivalent forces. In this case, the equivalent forces are something like this, that are distributed moment equilibrated by local forces. The direction of this distributed moment depends on the direction in which you want to apply the imperfection. Eurocode doesn't give you any help on this type of imperfection, so you can do whatever you want. You can put, for example, the distributed load in the same direction, or you can put in the opposite. It's up to you. You must define the more severe case. Pay attention that these loads depends on the actual force. In this case, the force on your frame in this case the actual force on your member. So you will have Q1 that depends on the end with 1, Q2, Q3. You can have very different value of the distributed load on each columns. If you do this kind of implementation, and you perform a second order analysis, you don't need to use the stability check. So you just go in the most stressed element and calculate the safety factor, that is just the actual force divided by the resistant force plus bending moment divided by bending moment. Because you consider this stability by second order analysis and local effects by this local imperfection. So you don't need nothing more. It's a resistance check. But the second option, that is the more common used option, together with the third option, you could say put imperfection, but only global imperfection, so no local imperfection. We have global plus local. Here is just global. Perform a second order analysis you have to check, take your element and do the stability check, not resistance check, but stability. So you have to consider buckling by the key factor, local effect by the K factor, and lateral torsional buckling by the key LT factor. But you could say, if you perform a second order analysis, you don't need to understand what is the buckling length. So you don't need to calculate the effective length, but you can calculate directly the buckling of this column by using this as the buckling length. So this K factor will be, if we have double T columns, a flexural one with the geometrical L. So you don't need to calculate the effective length. This is admitted by the code. Pay attention that this is not, these results are really lower than this. So this frame can carry a greater capacity than this frame, because with this method we underestimate the buckling effects, but is admitted by the code. Another method is always this global frame, perform first order analysis, this time using the same equation, but you have to calculate the buckling length that is greater than the geometrical length. So the length this time will be something that is greater than the geometrical length. How to calculate this effective length? By using the buckling analysis. From the Eurocode point of view, these three ways are the same, but I will show you next time in a practical case that we will obtain a very big load carrying capacity on the second case, but from the Eurocode point of view you can use it. Then there is also a method that is called as the general method that combines second order effect and the buckling effects. This method gives us same results of this one, different from this, quite similar to this one. The most common used in the past was this one, where they performed first order analysis manually or by very simple software, and the effective length by using some graph that are called the Wood graph for the effective length. Now we can just use the buckling. If you want to be sure and you want to stay from the safe side, the useful thing is to perform a second order analysis, and instead of using the L as the geometrical length, using the L depending on the buckling factor. Avete visto questa lezione, i metodi? Okay, we will see next time.